Alright, hello. Okay, here I am. Okay, I actually just migrated from Twitch, but I'm just telling everyone that I'm live in a moment. I could do your homework if you want. I mean, I could guide you if you like. Uh, hmm. But right now, this is just a test run on live streaming on YouTube, actually. So let's check it out. You can send your questions on that Gmail that I posted over there, on the top over there, and see if I could solve it. Math and physics questions, by the way. hmm Let me see if I could do this. Hold on. First time doing this on. Oops. Here we go. First time doing this on YouTube. Mm. There we go. I just sent it to my friends. Let's see what happens. Mm. Check out. Damn it. This sucks. Oh well. Well, anyway, yeah, the gist here, the purpose of the stream is basically just doing homework. Um, right now I could do yours, but, I mean, I could do yours, yes, but right now I'm just doing what I think is fun. What is fun for me, that is. So I already solved this problem, though. This one right here. Okay, my tablet works, very good. Last time on Twitch, I actually did this. I already solved that. And this one, where's the other one that I was trying to solve that I failed to? Look at the chat again. It should be here somewhere. It is. Oh, here it is. Found it. Nice. This one. Yeah, I solved this. Oh my goodness, this was actually a fun one. Hold on. Got it over here. Okay. This was actually a fun thing to do. Let me see if I could do any more problems that Discord offered me to do. Do it for free. Or just for fun, you know? Let me see. Oh, let's put on some music, by the way. Do do do. About this. Yep, this one. Okay, cool. Ah, that's soothing. I think that's a bit too loud. Hold on, let me check the stream. Yeah, it's a bit too loud. Check the stream. 1. Oh my god, I see that feedback loop. Oh well, that's fine. Good. Okay. Looks like I could do a little bit more. There we go. Yeah, that's a bit too loud. Too loud right there. That's fine. Hello, hello. Yep, good, very good. Okay. Now we can get started. Let's do some problems here and there, and we'll see what I could do. Check it out over here. You know, yeah, why do I keep clicking that? Here we go. No need for this, no need for that, no need for... Oh wait, I do need that. And plus... Nope, not that one. This one, yes. You, get over here. Yep. Nope. Control Y, I mean. Very good. Control Z. No need for that. And this one. Good. And, hello, how are you doing? I'm just doing some homework. I mean, other people's homework. But hey, it's just for fun, like I said. And, let's see what I can do. I could always solve the one that I already did. Like, for example, this one. Yeah, this one. I already solved this one. I could always do it again. So let's see. Let me check here. Oh no, that's a lot of stuff. Here. Watch this. I'm gonna erase everything and start all over. Here we go. Erase everything. I like doing this problem anyway. You're gonna search up some problems to find? Yeah, go ahead. Let's see if I can do it. But don't search up the ones that I cannot solve. Actually, that anyone can solve. That anyone cannot solve. Like the Fermat's last theorem. That's a proof that no one can do. Okay, so here we go. So let's get some notation right here. We got acceleration going that way, as you can see over here. Whoops. As you can see over here, acceleration is going from here towards the right side of the table and going downward. So I can see there's masses over here, M1, M3, and M2 in the middle, just sitting on the table. And we're trying to find the acceleration of this entire system. So let's try to do that. What I usually do is just focus on each masses. So I'll focus on M1 first. I already have the notation. What you don't know what this is, but yeah, I know. But it's just finding the acceleration of the object. That's all. It's pretty simple. So let's just walk through it. Watch and learn. So we need to pretty much balance the forces. So T1, 2 is going at the positive direction, so that's a positive. You can just make it a nothing there. And minus M1g, because gravity is going downward, opposite of this acceleration. And is equal to M1a, which is the net force of this mass M1. Cool. And that's your first equation. Very nice. Now let's look at the second equation. M2, mass M2. So we are given that T12, the tension 1, 2 is going backwards of the acceleration. So this is going to be a negative. And after that, we're going to have a... Oh, this one actually, this M2 is actually experiencing a frictional force. So it's going to have a kinetic friction going backwards. So this would be the coefficient of kinetic friction times m2g, and it's going backwards, that's why there are the minuses. And it's going to have a tension that is going the other way, the positive direction of the acceleration. So it's going to be positive t 2, 3. And it's also equal to the acceleration of the object. So it's m2a. Cool, that's your second equation. Now let's look at mass 3. Mass 3 will have tension that is going backwards of the acceleration again. So it's going to be t negative t 2, 3. And its gravitational force is going to go downwards, which is the positive direction of the acceleration. Therefore, plus m3g is equal to m3a. Awesome. Now that we have all of the equations that we have, we can manipulate and plug everything in onto one equation. So let's do that. Let's manipulate this. Turn into 1, 2 is equal to m1a plus m1g. Cool. We'll call this equation 1. Dot, dot, dot. This one as well. Manipulate this, and you'll have isolate t tension 2, 3, and you'll have t 2, 3 is equal to m3g minus m3a. Cool. We'll call this equation. Let's call this equation 3, where this one is equation 2. All right. Now we've done our simple algebra. All we have to do is just put 1 and 3 into 2. Plop. There we go. And we will have the following. We just plugged equation 1 in. You would have negative m1a plus m1g, these are all parentheses, minus mu k m2g, and then we add equation 3 into here. We would have m3g minus m3a is equal to m2a. This is very slidey. There we go. Very good. Okay. Now that we have everything in one simple equation, let's manipulate and isolate a by itself. We'll do that. m1a minus m1g minus mu k m2g plus m3g minus m3a is equal to m2a. Now we'll put everything on the right hand side, I mean the accelerations of the like terms on the right hand side, and we would have this m2a minus plus m1a plus m3a, and we would have this one minus m1g minus mu k m2g plus m3g. Stop it. Stop the memes. I'm doing homework. Okay, so we isolate A by itself over here. M1 plus M2 plus M3. Acceleration outside. And looks like we could isolate G outside over here. So we'd have M1 minus mu K M2 plus M3 and then G. Now finally, we could isolate A by itself. And lo and behold, we would have the equation M1 minus mu K M2 plus M3 plus M3. Over M1 plus M2 plus M3. And there you go. You have your acceleration of the entire system. Look at that. Very nice. That's the equation for this. And you could just plug in M1, M2, M3, the G constant, and the kinetic coefficient, friction. Let me do that real quick. So you have M1 is given to you, M2 is given to you, M3 is given to you. What else? Coefficient of kinetic friction, and G. Let's see what those are. 1, 2, 3. 10, 60, 45. 10, 60, 45 kilograms. This is 10 kilograms. 60 kilograms. 45 kilograms. Static kinetic friction, I mean not static, kinetic friction is 0.12 as seen over here. So we'll do that. 0.12. And G is 9.81 meters per second squared. Alright, awesome. So we just plug all of these in, and you have your acceleration. So I'll look at my trusty Desmos. Very good calculator. And it's gonna look like this. Pop up, and then divided by dot, and negative M1, 10. Negative 10 minus 0.12 times M2, 60, plus, what is M3? 45. Speed times 9.81. Good. For the acceleration of gravity. And M1, M2, M3. Okay, we're just doing this again. So, 10. Where's the plus? There we go. Plus. It's very dark. Okay, good. 60 plus 45. And the acceleration is... Oh, we're gonna make me do proofs? Oh no. Okay, fine. I could do proofs, I guess. Sort of, maybe. Okay, so the acceleration that was given to us is 2.37. 2.37 meters per second squared. And that is your final answer for acceleration. Nice. Very cool. Let's see if I made a mistake somewhere. Negative 10. It's 45G. And then 10, 60, 45. Whoa. Hold on. $10, 60, 45. Okay, good. I did it. Nice. 2.98. Oh wait, the guy got 2.98 meters per second squared, and it doesn't have units, so 0 out of 10. But here, I got 2.37 meters per second squared. I wonder what he got wrong. You probably, let me see, 2.983. You probably made one of these probably made this a plus instead. So let's see what happens. Let's see if he did. Probably a mistake on his part. No, that's not the case. What if I do the other one a plus? What if I make this one a plus right here? This one. That was probably his mistake. Let's see. Nope, that was not his mistake. Okay, that was bad. I'm trying to figure out his mistake. It's... What if I make this one a minus? Let's see, like one of these, a minus. We'll see. So we have minus 2.87. Okay, very close. How about you? Minus? Nope, that's not close at all. How about you? Minus 10.9. Looks like his only... Yeah, his only thing is that making this a minus was his mistake. That's probably his mistake. Or he didn't probably get this equation at all. I'm not sure. Unless he got this one right here. Let me check. 9.8. Okay, well, I know that's wrong, but it's basically the same thing. So, okay, 10 plus 60 plus 45 is good. So, 81. Very nice. Okay. That looks fine. So yeah, this is how you solve the problem on the acceleration part. Acceleration of this entire system. And it looks like since this is going positive, therefore our choice of direction of the acceleration was correct. Therefore, it's going this way. It's gonna all these blocks will be actually M2 will be sliding this way. M1 will be going up, and M3 will be going down. There you go. That's pretty much it. That's how you prove it. Pretty nice. Okay, let's see if there's any other problems. I'll check the email if there's any problems. I don't know if you sent one already. I don't know if you sent one already, Small Bean, but let's see. Nope, you haven't sent one yet? Okay, I'll just keep going on my own equations. I mean, problems. Let's check it out. That one's too easy. I want a challenge. Oh, you sent one on another place. Okay, cool. I could do that. Okay. Let me see. Oh, wait. I should check it out on the PC instead. Here we go. Should... Here. Hold on a moment. Got it. And got it. Okay, and then go to Gmail. Yep. Okay. Should be... Oh, here you are. Got it. Okay, what is this? Uh, ooh, okay. Well, I need to know my, what is it called? I need to know my properties. But let's see what happens. I'll attempt to do this one. Control V. So we can do this. There we go. Awesome. Can you see that? Let me see. Yep, you can see it. Good. Okay. If two sides of two adjacent acute angles are perpendicular, then the angles are complementary. Okay. Let's do this. What's this? There we go. Okay. If two sides of two adjacent acute angles are perpendicular, then the angles are complementary. Two sides of two adjacent acute angles. Okay, so it's like if two sides are adjacent and they're perpendicular, they're complementary and they make a right angle. Okay, that's basically what it's saying. Good. Given BA perpendicular to BC. So looks like proof step 1, it looks like you have to do the given BA perpendicular to BC. Line BA right here, this line right here, is perpendicular to BC, line BC. And let's see. This would be the, I forgot what this is called. Shown. And this is proof. I forgot what it is. Shown and proof. Oh, claim. That's what it's called. Claim. Claim. And this is proof. There we go. And this is given. And then number 2, it looks like, oh, it's right here, the rule. So all I have to do is just put that in here. BA and BC are so we have BNB. Oh wait, if two sides of two adjacent. Oh yeah, I forgot about that. So we have some sort of angle between them. Okay, that's good. And I need to name this thing. I need to know what the name of this one is. So we could say line B. No, that doesn't make sense. Line B. Two sides of adjacent. Two sides of. Okay. Let me say this one. How do I do this? It's like AB. They didn't name this, so AB. I'll just call this D. I need to have that point over there. So AD. So right here. Oops, got red. Angle ABD is adjacent with angle CBD. Then the angles are complementary. Angle BC and DC. Oh wait, I know that. This is supposed to be angle 1 and this is angle 2. Here, let's organize everything back again. Organize everything back. Let's start over. So we have angles. The claim would be 1 and 2 are complementary. Oh wow, it's that easy. That's it. That's all you need to do. Angle 1 and 2 are complementary because two sides of adjacent acute. Man, my handwriting sucks. Angles are complementary. Are perpendicular. I'll just I'm not gonna write that entire word. There you go. That's the perpendicular word. And there you go. It's done. QED. Yeah, it was that simple. Wow. So you don't really need this point D anymore. Okay. Well, I need to memorize this. This is pretty fun. Because this thing is already given to you anyway. So so you can prove that these two are complementary. Very nice. Yay, I know, right? Yay. Pretty nice, pretty good. I remember there's some sort of complicated ones like oh wait, I'm not gonna get into it because I don't know it by heart. It's a bit it's like this. It's like you're figuring out that these two sides are what is it, congruent. Wait, congruent? Yeah, congruent, yeah. Like they're the same. Where this one is the same and right angles are over here. It's basically meeting this. Oh, okay. It's basically trying to figure out if these two triangles are congruent. That's pretty much it. Oh, you have a problem too? Okay, I could do that. Let's check it out. I'll do it with a different color. Red is too bright. When did I start? 12:30. Okay, yeah. For now, let's check Discord. What is this? Oh, that kind of problem. Okay, we'll see. Hold on a second. Let me see if I could copy it from chat, by the way. Oh, I can. Good. Here we go. And you should be over there. Yeah. There we go. Where's my... Oh, here we go. Scroll bar. There we go. Awesome. What does it say? It takes 10 road workers 5 days to complete a road repair when working 2 hours a day. Working the same place, how many days will it take 2 people working 5 hours a day to finish it? That is a mouthful, but looks like I could do it. Yeah. So we have... Hold on. Okay, good. Takes 10 road workers, 5 days. 10, oh, come on. So we have 10. I need to make it smaller, hold on. 6, 5. Good. Takes 10 road workers. I'll just call them RW. 5 days. 5D. To complete a road repair when working 2 hours a day. 5 days, 5 days, 2 hours per day. So that means this is equivalent of, wait, no, hold on. 5 days times 2 hours per 1 day. So therefore, this is 10 hours. Cool. This is 10 road workers, okay? 10 road workers, 10 hours. Okay, this makes the problem much simpler. Working 2 hours a day. Working at the same place, how many days will it take 2 people working 5 hours a day to finish it? Okay, so looks like judging from the proportion, 10 row workers, 2 hours a day. Then we have 10 hours. So it looks like 1 road worker per 1 hour then. So therefore, proportionally, 2 road workers per 2 hours. Let's see if this logic works. 5 hours a day instead. So we have working at the same pace. How many days will it take 2 people working 5 hours a day? So we could do 2 people working 5 hours a day. Yeah, this is a mind boggler. So we have 2 people, 2 row workers, and then that means 2 row workers per hour. 2 hours a day. 5 hours per 1 day. 1D. And we got some time over here. The day, I'll just call it day, D. And then working, got the proportion right. So we have 2 row workers per 2 hours. And let me organize my thoughts here. It's all over the place. 5 days. Complete a road. Repair. Working 2 hours a day. Okay. Working at the same pace. How many days will it take? Yeah, it's just that the question is all over the place, so I'm trying to, my mind is all over the place as well. How many days? Okay, we're trying to find the days. Good. It'll take 2 people. I know, my brain is going wild too. So it looks like I won't be needing this. The proportion over here would be good for 10 hours or 5 days. And then so that's 10 road workers. 10 to 10 ratio. Okay, we need to figure out on ratios instead. So 10 row workers is 10 hours. Good. So that's 1-to-1 ratio. And then 2 row workers instead. Here we go. This is the proportion. So 10 row workers can do 10 hours. Cool. Oh wait, no. 10 row workers can do 10 hours. How do I, hold on. I could do this, So that's 1 day. Good. 10 hours. Good. What is the proportion? Damn. Ah, oh my god. Hold on. This is mind-boggling. Hold on, mate. This is actually giving me problems. Okay, five days, and then 2 hours a day, 10 hours. Okay, good. Now after that, you have two row workers working 5 hours a day to finish it, and then 5 hours a day, and you have that. Mm. 10 row workers, 5 days. Proportion is this thing. His music is not helping. um, hmm. No, it's not hard. It's just that I'm going everywhere. So yes, it's hard. um, hmm. I just need to figure out how to maneuver this. 10 road workers. How much time do I have left? 114. 5 days. Okay. 10. It's gonna be 5. Let me just look at it at a visual perspective. So we have 5, and then this would be 2 hours a day. It's all in one day. 2 hours. All together. Good. 2. I could do 1 hour for each of these. Okay. Divided by 5. 1 hour. Okay. Okay, we need to figure out how many hours can be taken out. Not how many hours, like how much time can be taken out for adding one worker into this. And then we could find a proportion. There you go, much better. So from here, you have 1 hour over here. This is for 1 day, by the way. 1 day, 1 hour, 1 hour. And then it's going to be 1, 2, 3, 4, 5. 60 minutes divided by 5. Then, 5 workers, row worker. Let's check it out. This would be 12 minutes. Yep, that seems about right. Yep, 12 minutes. So 12 minutes each worker can be added. So let's see. Each worker, it's gonna be minus 12 minutes each worker. Okay. Each worker. We'll do that instead. So that means okay, I understand now. This is what you need to do. Is equal to 10 hours. So this is the completion is 10 hours. Completion. This is one example of a completion. It took 10 hours to do everything. Cool. But what about when it takes 2 row workers? It takes 10 hours to complete everything. Good. Wait, hold on, sorry. It takes 10 hours to complete everything. And working 2 hours a day. And that means days is equal to 2 days. Okay, that doesn't make sense. Nope, that doesn't make sense. 2 days. Yeah, it's like 5 days over there. Yeah, that doesn't make sense. Oh well. This is completion. It takes 10 hours to do that. Good. And going for disproportion right here instead. How do I efficiently go about this problem? Because right now this is not very efficient what I'm doing right here. But I guess brute force is all I could do for this one. 10 row workers, 5 hours to complete. 2 hours. Okay, good. So 10 row workers is to 10 hours. And then what about 5 row workers? That means 20 hours. Good. What if I do this? 5 row workers. Okay, what about if I divide by this by 5? Then we have 2 row workers. And it times this by 5, you got 50 hours. Okay, times this by 5. So that means 50 hours, yes. So that means right here is going to be 50 hours. And then days to you can manipulate this. 50 divided by 5 is going to days. It's going to be 10 days. Okay. I think I got it. 10 days. It takes 10 days. I'm just going by the proportions right here. Oh my god. Yeah, it is a mind boggle. Okay. So 2 people working 5 hours a day. It takes 50 hours. Okay, as long as you know the proportion, it looks like that it takes 10 row workers to do 10 hours, right? And you can just ignore the days part first. Okay, it takes 10 row workers to do 10 hours. And if you half that thing, okay, so see, so if you half that thing and you, or even multiply it by 5 and you times the hours by 5, you would get the proportion. It's going to be 2 row workers for 50 hours this time. Very nice. It's all about proportion. So after that, you just so it takes 2 row workers to do 50 hours. And you equate the days times hours per day is equal to 50 hours. And manipulate it to isolate D by itself. 50 divided by 5 is 10 days. So therefore, 2 row workers for 5 hours per 1 day takes 10 days. And lo and behold, that's my final answer. Oh my god. So you don't even need this. You don't even need that. You could just do these guys. There you go. That was terrible. Thanks for the question. Yeah, that was a mind boggle. Have a fun eat though. 2 row workers for 5 hours per day takes 10 days. There you go. Much better. Ah, the mind boggle is real. Okay. I'm drinking water after this. Ah, okay, good. Okay, what else can I do actually? What is this? Hmm. I could always do this one. This seems fun. Get this question out of here, please. Okay, got this. Control V. Let's monitor. Okay, and here we go. An organ pipe closed at one end and open at the other has a length of 45 centimeters. What is the longest possible wavelength in meters for the interfering sound waves that can form a standing wave in a pipe? Okay, makes sense. So I could illustrate this real quick. We got closed on one end and open on the other. Sorry. So it looks like that, if I recall, let me look this up just in case. If I recall, let me see. You could look up closed pipe wavelength, and gonna have that thing. Yep, there it is. Good. It's gonna be. Alright, here it is. You're going to have a node of the wavelength over here, and it's going to be open over here, like that. So for example, like this. Yup. And then yup. Or you could have a node right here, and it's gonna look like that, and like that. As long as there's a node at the closed end and an open at the other end, where the pipe is open, right there. But it wants the longest possible wavelength for this pipe. And L is given to us, so we have it right here. Wait, let me just remove that node over there. Yep. Nice. L is given to us is equal to 45 centimeters. So that means that looking at this, the only longest possible way is to have only one node as opposed to 2 or 3. And this gives us half the wavelength. So if you continue this, what is it half? Let me check. Half the wavelength. And then it looks like, yep, half the wavelength. Good. It's gonna give us half the wavelength. If you continue this wave over here, it's gonna give us half. Kind of a rough estimate of what it looks like, but yeah, that's basically it. As opposed to having 2 nodes, I'll show you in a moment. As opposed to having 2 nodes, meow. Do it again. As opposed to having 2 nodes, the wavelength is right here, so it's shorter. Look at that. The shorter wavelength. It looks like this case it's gonna be 3.5 of the length over here. Wait, no, not 3.5. 2. Hold on. The length is gonna be yum. Yeah, 2/3 of the length. There you go. 2/3 of the length. Nice. Let me check again. 2 and then yep, 2/3 of the length. Good. So that's actually lower than half of the length would be. So let's demonstrate again. going to have one strong wavelength over here, one other strong wavelength over here. I mean the line. And this would be half. It's like all the way over there. There you go. Much better. Let me draw this better. Pew, 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 pew. So we have this thing. Let me just measure it with my hands. So the node will be right here. So therefore, there we go. That's what it's gonna look like, roughly. So therefore, it's half the wavelength. So it's half of 45 centimeters, and it's gonna be divided by 2 centimeters. It's equal to wavelength. 4 equals 22.5. Yep, that's it. 22.5 centimeters will be your maximum wavelength of this entire system. Of this system, yep. There we go. Much better. Orville wavelength? Let's check it out. So you have quarter. So it's look like this, you mean? Let me check again. So if I extend it even further, let's check. And if I extend it backwards... Hold up. You have a good hunch. Yes, that's probably a quarter. Let's check. So you have... Yep, it is a quarter. Oh my goodness, I just compensated for half of it. Okay, so it is a quarter. Damn. So it's gonna be 4 instead. Poo poo. And then it's gonna be... Aw, I just halved it. That's all I did. Blows. So it's gonna be like this. Hold on. It's gonna be 45 divided by 4. You have divided by 4, and it's gonna be... Oh yeah, no wonder. Yeah, you're right. So it's gonna be 45 over here, and 45 over here, and then you have a 45 over here. So that means it's 45 times 4 instead. Wow, that's even better. No wonder it was like a bit iffy. Alright, thanks, Glenn. So it's gonna be 45 times 4. It's gonna be 8. I need 180. Yep, 180 centimeters. Nice save. Wow, totally forgot about that one. I should not pick this problem. That's okay. It's good to remind me. Solve these problems will just improve me even further, and that's pretty much the gist of this stream. Okay. So, alright, 180 centimeters. Yeah, that's it. Nice. If I go further, yeah, it's gonna be smaller. If I put nodes over here. Okay, that does make sense. Okay, cool. Hey. What's up? I'm only gonna stream until like, what is it? How long have I been streaming? Since 12? Yeah, I'll be streaming until 2. That's pretty much what I'm doing. Okay, what else? What other questions that could screw me over? I need to buff up my stuff. That's all. So let's see. Shortest wavelength? 0. It just goes to infinity if you have infinity nodes. Like what I'm saying, like infinity nodes right here goes over here. So I can't really see what the what's the shortest one. Let's check. It just approaches 0. That's all it is. That's the wavelength. Why is there chemistry in the physics channel? That's weird. Okay. I'm just trying to look at the Discord and see what I could do. What are things I could do? Oh yeah, someone sent me a question. Should I do it? I don't know. Kind of iffy about it. Let me check. So let me see. Where's the question? Okay, did that. Nope, I did that already. I mean, I always wanted to, I wanted to do this actually, but I already did it off screen. So, yeah, this is a question that was sent to me. Oh boy. And your final answer is your potential over here. Very nice. Pretty cool. Let me see. So this is the potential outside of the sphere, and exactly at the sphere, exactly at the surface of the sphere, and this would be inside of the sphere of its potential. It's a pretty nice derivation, actually, as you can see over here. Pretty cool. This is what it looks like. Pretty nice derivation. Now here's this one problem that I always loved. I could just share it to you guys. That's why they changed the size of the trumpet to hit lower / higher frequencies. Oh yeah, that's nice. I don't know much about instruments, but yeah, that seems cool. All I know is that octaves, correct me if I'm wrong, but octaves has this equation. So you have so the frequency at a certain octave, it's going to be 2 to the power of n. Let me check. 2 to the power of n. Nope. Times 2 to the power of n. So if you increase the octave by 1, you go positive direction of n, and it's going to increase the frequency by 2. There you go. Frequency times 2. Or if you decrease the octave by lower, so you just do -1, so you decrease by so you decrease the frequency by a half. So for example, if you want to lower your octave, -1, so you have frequency divided by 2. There you go. Or if you want to up your octave, like you want to do it 1 octave up, you could increase it by 2, so your frequency will increase by 2, times 2. This is the equation I saw. I'm not sure if this is true, but this is what I deduced. So this would be your frequency, yeah, final. That's the only thing that I could see on the increasing octaves. So yeah, if you increase your octaves by twice, you'll have 4 times the amount of frequency. Yeah, it seems true, right? I mean, as far as I could see. But okay, I could always share you a different problem. Just trying to find one. Can't really see. Oh wait, my music. It's gone. Oh no. Yes. Then, oh, it's different music now. Okay. So I always like this problem right here. See if I can make another loop, and then right up there. Let me see. There we go. So let's say that you have an infinite plane. Like this. I'll just zoom in a little bit more. Dum, and then right here. So let's say that you have an infinite plane. Very nice, infinite plane. And you have a particle that is a positive right here, Q. And this plane right here is rounded. It's an infinite plane going that way, this way, this way. Cool. And you're trying to figure out what is the force that you needed for this particle to go downwards. It's actually a pretty fun problem. So you know the point charge. Point charge is gonna have a force of this. Let me see. Gonna have a force of just a point charge. Here it is. I just don't want to mix it up. Here it is. F is equal to 4 pi epsilon naught. And Q, Q1, Q2 over R squared. This is actually what you needed to solve this, actually. But you need to have some sort of tips and tricks for you to solve this problem. So you're trying to find the force that is needed to go down onto this infinite plane that is grounded. So how would you do that? Well, apparently, there's this trick called the laws of images, where you could have a instead of a plane, a charge in a plane system, you could actually simplify it to being a charge and equal and opposite way down below. So you'll have an imaginary charge that is down below. So let's say, for example, that this distance d over here to the perpendicular to a plane, and over here also have a distance d, and it's equal and opposite. So therefore, this is also distance d. Very good. And now you change the system from being a point charge into a plane. It now turns into a point charge system. Look at that. And from here, you could just put both of these boys into this equation, and you would have your force. So your force equivalent is going to be F4 is equal to 4 pi squared. Epsilon naught. And Q1, Q2. They're the same charge, so it's going to be Q squared. You could have a minus 2. But all I wanted is the magnitude anyway. And R is the distance between them, 2d squared. And lo and behold, we would have 4 pi epsilon naught over -1 Q squared d squared. Oh, how do you know Q2? It's just an equal and opposite attraction of these two charges. So they're both the same charge. And it's going to be, I'll remove this. And this would be 16. There we go. And you have your force. Now the reason why this works is because both of these systems actually have the same boundary conditions. And if they both have the same boundary conditions, they would have the same solution. That's basically it. It's pretty nice. Like, for example, the voltage in between here, since voltages are voltage, or what is it called, electric potential on the middle over here, as right here, is going to be V equals 0. It's because that if you sum all of the voltages or electric potential onto this part of the distance between them, it's going to be V equals 0. So that means that the boundary conditions are the same. Therefore, the solution will be the same. It's pretty nice. You someone send me something? Nope. Okay, good. So we could actually find the voltages if you want, or electric potential. I'll just call it electric potential. So we want to find the electric potential over here. I'll just call it P, or anywhere if you like. P over here, P over here. It's basically a general electric potential. So all you have to do is just, of course, change it into a 2-point system find the electric potential from the positive Q and the negative Q. And the electric potential equation is going to look like this. Or pi epsilon naught over, where's it? Here you are. Q over R. Nice. And there we go. All you need to do is find the electric potential from the positive direction. So it's going to be V is equal to, I'll just put 4 pi epsilon naught on the outside. Q is a positive. And R would be a distance from Q, so it could be right here. And I'll just call this like this. It's like X direction, Y direction, Z direction. That looks good, yeah. So going this way, it's going to be, you could just use the Pythagorean theorem, so it's going to be x squared plus y squared plus, so from here, a distance d, z direction d minus c. There you go. D minus c, I think d. Let me check again. So you got that. Yep. Z minus d? Okay, let me see. D minus z is possible. Okay, good. So we have a square root over there. That's pretty much going for the radius from distance from here to here. So I'll call it r. And after that, we do the same thing for the negative charge. So minus q, because it's a negative. And same thing, x squared plus y squared plus d plus z this time. Squared over square rooted. And that is your electric potential everywhere between the plane and the charge. Pretty nice. It's a pretty awesome solution. And of course, keep in mind that this charge that we put over here is imaginary. So we don't really care what happens below the plane. We only care what happens above it. That's it. So just keep that in mind. It's pretty nice solution. I'm kind of contemplating whether that it's this or that. Let me see what the solution says right here. Let me check. Images. Where's the images? Nope, it's not you. And yeah, that's it. Okay, good. I mean, we could always check, actually. I should have not done that. So let's say, for example, that, these are switched, by the way, for some reason. Let me see. Z minus D. I mean, it's going to be destroyed anyway, whether it's minus or plus. But let me check. So let's say we could find the potential that is right here. We expect that V equals to 0, right? So the origin is right here, by the way. So the origin over there. It's going to be 0, 0, and then 0. D squared is D. It's going to be Q divided by D minus, over here, 0, 0, 0, and then Q minus D. Okay, makes sense. So it's going to be potential going to be 0 is over there. Very nice. Okay, very cool. But what about if it's over here? Let's check it out. So P is over here. P, oh, that's too dark. So P is over there. Let's see what happens. So q over x and y is going to be 0. Yep. And then all we left with is square of z minus d. So it's z minus d minus q. Same goes over here. 0, 0. D plus d. D plus z. And that's good. Let's check it out. It's all not over 1, 1. Okay, 1 over that. Okay. So we are left with this. Hold on, let me see. So z minus d. Got that. It might be very cool. And d plus c. Very cool. Ah, okay, so this is the perspective of that guy. Makes sense. D and then plus C. Okay, makes sense. So this potential is actually at the perspective of the plate itself. So that's pretty nice. We have a z minus d over here. So z, I'll just say z over here, and then minus d. You're gonna have right here, c minus d. Oh yeah, okay, makes sense. Gonna have a minus. Yeah, it's gonna have a minus though. Okay. And then z plus d from the imaginary number over here. Where is d? D plus z. And that does make sense. Okay, cool. So these conditions hold. Very nice. It's pretty cool. Pretty cool solution. So you can actually just do this with finding the electric field. Yep, electric field and energy as well. It's a pretty nice solution. So you could do potential. Oh, whoops, that's not a vector. Potential and the force. There you go. Force, potential, electric field, and energy that it takes to move this particle towards the plane right here. Pretty nice. Okay, very cool. Pretty cool solution. Now you could actually encounter a lot of complicated ones, like for example, a charge plane right here. It's perpendicular, and you have a positive charge over here. I'm not sure if you needed a imaginary charge over here, over there, and a positive one over here. I'm not even sure, but I know I encountered this before, but this is actually a very good anomaly. Very good problem too, if I recall. But it does require the point charges over here that we've mustered, and doing it twice for each one, if this is the solution though. Seems about right. Pretty nice. Oh well. This was a good run. Let me just Control S. This looks like a mess. What are things I could solve for, what is it, 7 minutes? Let's see what happens. Something that is not too difficult, not too easy. Let me check. Interesting. Weighing that high. Okay. Ah, I could do this one. Seems pretty simple. A nice send-off to a nice send-off to this stream. I think it's too simple though. Whatever. Control V. Nice monitor. Go. This is what I could find. Okay, here we go. So a child and a sled weighing 209 newtons slides down an ice-covered frictionless hill that is 10 meters high. At the bottom of the hill, there is an ice-free, rough horizontal surface that brings the sled to a stop within a distance of 25 meters. What is the coefficient of friction between the sled runners and the horizontal surface? Okay, so it is pretty simple, straightforward. Going from A to this is too much. Let me change my brush size. There we go. Okay, going from A to B, we can do the conservation of energy. So PE initial plus KE initial is equal to PE final plus KE final. Actually, we should denote them as A and B. So the potential energy at A and its kinetic energy, and potential energy at B and its kinetic energy. Good. So initially he was at rest, so that means kinetic energy would be 0 because velocity is 0. Because velocity is 0, call it that. And right here, since it's at the bottom of the hill, potential energy would be 0 because height is equal to 0. Good. And we know the usual potential energy equation. So it's pretty much mgh. Hold on, let me see. mgha. Yeah, there you go. And newtons is already given to us. The mg is the newtons. So I'll put that later. Hold on. 0 plus ke. It's pretty much the classic half mv squared. Very good. This would be at B. Yep. Putting this all together, mg over here is 290 newtons. Hold on, whoops. There we go. Very good. And we have this guy. 90 times at newtons times, where's the height? 10 meters, yep. Is equal to half mv b squared. Oh, okay. So it looks like we could actually cancel this m out though. So we don't really could find m right here. 290 divided by 9. Yep. So we have mg is equal to 200. Hold on. M is equal to 290 newtons divided by g. Yep, 290 newtons divided by g. Damn, just give me the mass problem. Jesus. Okay. M is equal to 290 newtons divided by g. And so we have this over here times 10 meters. We isolate v by itself, so we got that. And oh, actually, we don't really need to do that. we could just skip everything. So we got the energy over here, and it's gonna equal to the half mb squared, and this would be at point B. Yeah, good. So now we're going from point B to C this time. I'll show you why we don't really need to solve it further. Point B to C. So from point B to C, all we need to do is half mb squared. We know that the potential energy at that point is going to be 0. And we're going to have the static coefficient, mg, yep, that's pretty much it, yep, mg and then x, coefficient over here, yep, mgx of the slide, distance of the slide, which is 25 meters, good, plus 0. Yeah, that's about it. Wait, no, this is a minus. Me minus 0. Good. And we know for a fact that it's 0 over here because kinetic energy will be 0 finally. There you go. And it's all going to be going down to the static kinetic friction. So putting this all together, we know that negative mu k mgx there we go. So putting this all together, we know that 290 newtons times 10 meters is equal to the kinetic energy at B, and the kinetic energy of B is equal to minus kinetic coefficient friction, mgx. Then we could just put them all together. Equation 1, call this equation 1, call this equation 2. We just equate equation 1 and equation 2 together. There we go. So all together, we're gonna have 290. Oh, by the way, this is 209 newtons. So I said before. Okay. So putting it all together, 290 newtons times 10 meters is equal to negative mu k 290 newtons times x. Oh, x is, what is it, 25 meters, yep. Manipulate, you'll isolate k by itself. I mean, mu k. So you have 209 newtons times 10 meters divided by what is it? Yep, 290 newtons times 25. And you'll finally have these guys cancel out. Bloop, bloop. And your static coefficient of friction is going to look like 1 over 2.5. What is that? What is that actually? Over 2.5. Oops. 10 divided by 25. 0.4. Look at that. That's your static coefficient. Your kinetic coefficient friction. Coefficient of kinetic friction. There you go. 0.4. Very nice. You could have a negative there too. Yeah. Let's see. Yeah, that's pretty much it. You got it. I don't know why there's a negative there though. If I look at it through notation. Oh, okay, I get it. You don't really need that negative. Because it's going towards it. It's not really going away from it. So there we go. And there we go. Good. So it's like adding into that friction that is going towards it. Okay, makes sense. Okay, cool. So static of kinetic friction. I keep saying that. The coefficient of kinetic friction is this one. And that's pretty much it. there you go. It's a pretty nice, simple problem. Pretty cool. Nice. Alright. Is this problem doable if A and B has friction? Let me think about that. Problem doable if A and B has friction. Did I encounter that before? Yeah, I did encounter it before, but I only did it for the case where it's a slope. I'm not sure if it's a curve though. Yeah, it is doable. And I did it with balance. Yeah, balance of friction. Friction energy. Yeah, the energy. Balance of conservation of energy. Yeah, same thing. With conservation of energy. I think I did that before. It's right here. Oh yeah, I did do that before. I recall. Let's check it out. You might have seen this on the Discord. This guy. So right here. Let me see. So you have this one right here. It's like a slope that is going, a friction slope going down, and it just goes up. There you go. Let me see. It goes down and it just goes up. So yeah, these are friction planes. It's pretty nice. Pretty nice problem actually. And you're using conservation of energy still, where you're subtracting the energy produced from the friction on each plane. But I don't know about slopes though. Slopes are pretty much I mean like this kind of slope, the curvy slopes. They're pretty much an anomaly for me. Were they the same? I'm not sure. You think they would have the same problem like this? Like that? Are they equivalent? I'm not sure. But the problem that I have gone through, it does require trig to get this correctly, though. So my hypothesis is no, they're not equivalent. But okay, I think that's it for today. But I'm pretty much pooped. I did this for 2 hours. So what did I do today? Today I did this thing and this thing that I've shown you, the laws of images, and this one that you corrected, Glenn. Thank you. What else? Oh yeah, I did some sort of problem that my little cousin gave me, and it mind boggled me. I don't know if this is the right answer though. Oh, thanks, cousin. Thank you. Thanks for greeting me. I think I did this right, but I'm still iffy about it. It's just a simple problem, but it just mind boggled me. You just take a screenshot if you want. You try it yourself. But what else did I do? Oh yeah, I did a little bit of proofs. This proof right here. It's already given to you anyway. Like little proofs. That's what I did today. And I did this one. Where is it? Yeah, I did this one again. I just showed it to my little cousin. Pretty nice proof. What did I do next? I think that's it. That's what I did today. That's all I did today. Here's the problem again, if you want to try it out. I said it takes 10 days. Okay, I think that's it for today. Thanks for coming. And yeah, I might do this again. I'm just testing the waters of YouTube to see if it's good enough. But it looks like Twitch is good enough for me though. Twitch. I gained like 10 viewers. I just wanted to have a audience. That's it. You guys are good though. You guys are great. But that Portuguese audience was pretty nice. It gives me a order of chaos, you know. Chaos is great for this kind of stream. But okay, yeah. I'll see you guys next time. I might do this again on either on either platforms, like YouTube or Twitch. We'll see what happens. Take care and happy learning. Stop recording. Stop streaming.